process that is involved in renal exchange is reabsorption. And reabsorption, I kind of begun describing this earlier, is where the kidneys begin to remove things that it wants, remove things that the body wants from the tubules and sends it back into the blood via the peritubular capillaries. So the peritubular capillaries are the capillaries that are wrapped around the proximal and distal convoluted tubule. And this is how we can take back things that we don't want to be excreted from the tubule, which is making urine, and send them back into the blood because the body needs them. Most of this happens in the proximal part of the tubule, so the proximal convoluted tubule, and most of this is not regulated. Now, when we say not regulated here, we mean that it's not influenced by any intrinsic or an extrinsic mechanism. It is freely happening. It doesn't increase or decrease in response to our hydration or sympathetic or parasympathetic. It is always happening at the same amount, at the same rate, and it is not regulated. Okay. So this table kind of depicts some of the things that are filtered and then aggressively reabsorbed because the body needs these things for one reason or other. So first thing is water, right? Most of the water that is filtered is reabsorbed. And this happens at a rate of about 180 liters per day being filtered, and then most of that being reabsorbed. We actually only excrete about 1 to 2 liters of urine per day. So in a healthy, well-hydrated adult, we filter 180 liters, but we only lose or excrete 1 to 2 liters, which is about 1% of that filtrate per day. Other things that are reabsorbed are glucose. So all of the glucose that's filtered is reabsorbed. That's really important. We should not see glucose in the urine unless we have high blood glucose. So diabetics will typically see some amount of glucose in the urine, but in a healthy person, all of the glucose should be reabsorbed. Urea is also reabsorbed to a bit of a lesser extent, and this is because this is needed for water reabsorption. I'll talk about that. So make an asterisk here by urea because the reabsorption of urea is crucial to creating the gradient that we need in order to reabsorb water. And then our other ions are also reabsorbed: sodium, potassium, calcium, chloride, bicarbonate, and those are aggressively reabsorbed. So most of that is reabsorbed, and we know that these are things that we need. We need our sodium, potassium, our other important ions at the relative concentration in our plasma in order to maintain our things like our resting membrane potential, in order to help excitable cells fire action potentials. We know that these ions are needed in certain concentrations, so we cannot just filter them and excrete them from the body. We must reabsorb them aggressively. Okay. And then we'll talk a little bit later on in the kidney, in this unit, about how bicarbonate is reabsorbed and how that plays into the acid-base regulation. Okay, so we're going to move on here to describe the mechanisms of reabsorption. We're going to talk specifically about one ion, sodium, which is the most important, but understand that other ions are being reabsorbed too. And so when we speak about solute reabsorption, we're talking about movement of important solutes from the lumen of the tubular structures, basically the lumen of the nephron, back into the blood. So it's important to understand this relationship here. We've got these peritubular capillaries that are wrapped around the proximal and distal convoluted tubules, and this is how we facilitate the reabsorption of important nutrients and ions back into the blood. Some of it happens in the distal tubule, but most of it is happening in the proximal convoluted tubule. And we'll move on here now to look at the barrier for reabsorption. So in order for these important nutrients and ions to be reabsorbed back into the blood, they're going to have to go through 3 structures. They're going to have to go through the epithelial cell of the renal tubule, through the peritubular space, and then through the endothelial cells of the peritubular capillaries. Okay, so let's kind of describe that here. So if we look more closely at this relationship, we've got the lumen of the tubule, which is here. This is where the filtrate is. We've got the epithelial cell that lines the proximal tubule. We've got the basement membrane of that tubule. We've got the peritubular space, which is a small space between the tubular structure itself and the blood vessel, the peritubular capillary. And then we've got the endothelial cell that lines the peritubular capillaries. And then here we've got the lumen of that capillary. So this is where we've got our plasma and erythrocytes and so on. So in order to effectively reabsorb the things that we need to move them across these structures. They need to go from the lumen here, across this cell, across this space, across this cell, and to get into this lumen. And so that's what we're going to be describing here. We reabsorb most of our filtered molecules, and I described what those are earlier. We reabsorb most of our water. So 99% of the water is reabsorbed, and we only excrete about 1 to 2 liters per day. Now, this will obviously increase in well-hydrated states and decrease in dehydrated states. So that 1 to 2 liters a day can look very different depending on how much fluid you're intaking. And you probably know this from your own experience or from prior knowledge, that if you're drinking a lot of water, your urine is going to be, 1, it's going to be more volume, but 2, it's also going to appear more clear, right? It's going to be clearer, less cloudy, and less concentrated. If you're drinking less fluid, right, if you're drinking less amount of water, or if you're in a dehydrated state, your urine is going to be less volume, so it's going to be significantly less, but it's also going to be darker, more concentrated, and probably more cloudy. It's going to be more solutes than actual liquid, okay? So that brings us to speaking about the obligatory water loss. So at a minimum, humans must excrete 400 milliliters of waste per day. And so that is the amount of fluid that you must excrete from your body, even if you're bringing in 0 fluid. So even if I'm in my most dehydrated state, even if I'm in my most dehydrated state, even if I'm drinking absolutely 0 water, every day I must excrete 400 milliliters of urine as a means of ridding the body from the waste. Otherwise, I'm going to get into toxic states because I'm holding on to that waste. So that is called your obligatory water loss, right? A minimum of 400 milliliters. And then 85% of reabsorption occurs in the proximal convoluted tubule, along with a descending loop of Henle. We're going to talk a lot about that in the next packet. And this is mainly unregulated, meaning that nothing is influencing this, neither your hydration status, nor any neurons or any hormones influences this type of regulation. Alrighty. So let's look at how these substances, these solutes, can be reabsorbed across those structures that I mentioned earlier. So the first thing we want to establish is that the osmolarity of the filtrate that's sitting in the lumen on this side and the osmolarity of the plasma that's sitting in the capillary on this side is the exact same. So we've got equal osmolarity, meaning that both of these solutions or both of these fluids are isoosmotic with regards to one another. So in order to get solutes to move from the lumen here back into the blood on this side, we have to create a gradient where there's some sort of change in the solute concentration in order for water to move down that high to low solute, that gradient, that water gradient, where water can move from a place of high concentration to a place of low concentration. And so what we do is we pump solutes from the lumen of the tubule into the epithelial cell and then into the lumen of the capillary. And so we've got a high amount of solutes here, a low amount of solutes here, and we can then facilitate water freely moving according to osmosis down its concentration gradient. So that's what we're going to move on to describe how we can actively and passively move certain solutes down their concentration gradient or up their concentration gradient, depending on whether it's active or passive. And then water will simply follow that gradient, okay? So the first thing in understanding that is that sodium is pumped from the epithelials, from the solute here into the epithelial cell. And then that sets up a concentration gradient that will then drive osmosis. So because we're actively transporting sodium out of the filtrate and into the peritubular blood, we then move water along because we've got more sodium here, less sodium here, meaning we've got higher water concentration here, a lower water concentration here, and then water can freely move according to its gradient. Alrighty, so let's speak about how the cells of the proximal convoluted tubule are adjoined. So we've got the apical side of this structure facing the lumen of the tubule. So this is the apical membrane. We've got the basolateral membrane facing the peritubular space. And we've got different pumps set up on the apical membrane and the basolateral membrane that are going to help create this gradient. So we know that the cells have a lower sodium concentration than the filtrate. And so due to the sodium potassium pump, so remember this is a typical epithelial cell, we've got a sodium potassium pump along the basolateral membrane that is pumping sodium out and potassium in. And so we have less sodium inside the cell than we do inside the tubule. So that creates a gradient for solute Y, which is sodium, to passively move into the cell. So solute Y is going to move into the cell according to its passive gradient, less sodium here, more sodium here, and then solute Y, again, sodium, is going to be pumped out of the cell according to the sodium-potassium pump. Now, because solute Y is permeable to the membrane, and it's also in the correct proportion to facilitate this movement, we have more sodium ending up here in the peritubular capillary, okay? The second part of this is the movement of chloride. So this first solute was speaking about sodium. The second solute, solute X, is speaking about chloride. So chloride is at a higher concentration in the cell and a lower concentration in the solute. So chloride is going to be actively pumped from the tubule into the cell, and then it's going to be passively moved from the cell into the capillary. So we can see here that solute X, chloride, is being pumped into this surface. And so because it's being pumped, it's going to build up in concentration inside the cell, and it's going to leak according to its gradient from the inside of this epithelial cell across into the peritubular capillary. So here we've got sodium and chloride making its way into the peritubular space, and then into the peritubular capillary. And so the big picture here is that we end up with more solutes being pumped or leaked into the lumen of the capillary. And then the third part of this is that water simply freely flows according to its gradient. So now we have more solutes here, less solutes here, and then water is higher concentration here, a lower concentration here, and so it freely flows according to its passive gradient. Alrighty, I hope that makes sense. Let's see if there are any questions. Okay. All right, so this is kind of an overview of that, showing the movement of these two solutes and then the movement of water. And then we also have solute Z, which can be any other solute. We're not going to look specifically at what this is, but you do have some ions that are present in high concentrations here in the tubular fluid, low concentrations here in the plasma, in the capillary. And so they can passively move. They don't have to be pumped or leaked. They don't need any transporters or any carriers. They can simply freely move from the tubular fluid into the plasma. So these are how some of our ions move. And these are how some of our freely flowing other molecules move. And then this is more importantly how water moves, right? The most important thing here is that we've got lots of water reabsorption from the tubule into the blood so that we don't lose water in excess quantities.